Alright, so let's get this last video for chapter 16 out of the way. First, I thought I'd just share what we did this weekend. We welcomed a new guy into our house. His name's Dakota, and he's pretty cute. And he's not being welcomed by everyone. As you can see, Clyde doesn't think much of him at all. So right now they're separated. Hopefully they'll learn to get along eventually. So enough of that. So just again going over what we've learned in chapter 16, we've talked about how Maxwell's equations predict the existence of light, which is electromagnetic waves that travel through even a vacuum at the speed of light. Today what we're going to focus on is the idea of that these electromagnetic waves, as they're traveling through space, they are carrying energy with them, and they're also carrying momentum with them. All right, so that's what we'll be looking at today. Just reviewing, remember the electromagnetic waves consist of varying electric and magnetic fields that are at right angles to each other, lying in different planes, and are both perpendicular to the direction of their propagation. They satisfy what we call the wave equation, which is an important equation in physics, and the solutions have the solution of a traveling wave that you might see or look familiar from the beginning of the semester. We also talked about the existence of the electromagnetic spectrum. While we often think of light as just the visible light that we can see with our naked eyes, electromagnetic radiation actually covers all of the wavelengths and frequencies down from radio waves all the way up to gamma rays, and what makes them different is although they all travel with the speed of light, they have different frequencies and wavelengths. Now, what we're going to be focusing on today is the idea that when a wave is traveling through space, it's carrying energy with it. One of the way that we sort of quantify that is through what is called the pointing vector. The pointing vector is basically a measure of flux. Flux is something that we see in physics here and there. Not a whole lot in general physics, but in general flux, you're always talking about some quantity that's passing through some area in some amount of time. For the pointing vector, it's energy. It's energy per unit area, per unit time. Because of the fact that it's energy over time is why they're saying it's power per unit area, because power is energy over time. So the pointing vector has the same direction as the propagation of the wave. It's defined as E cross B, 1 over mu naught E cross B. And so it makes sense that the direction of the movement of energy would be in the same direction as the movement of the wave itself. Now, one of the ways that we can think about this is we might remind ourselves that we look at expressions for energy density. One of these you haven't derived because we didn't cover that chapter, but way back when we talked about the energy density due to an electric field, turns out that the energy density due to a magnetic field looks similar. It has to do with mu naught. So if we think about the total energy that the wave is bringing to a space, it might help us thinking about the energy density at first. First of all, I just want to remind you that because E over B is equal to the speed of light, because that ratio holds for electromagnetic waves, we can actually express the total energy density as either all in terms of the electric field, or we can express it solely in terms of the magnetic field, using this as a substitute to write things all in terms of one field. In any case, let's think about the fact that we have a wave, it's passing through a certain area, and it has the energy density equal to U. And if we think about how much energy passes through this area in a certain amount of time, so the energy through A in delta T would be equal to the energy density times the volume. And that is, in a certain amount of time, if we allow the light wave to start right here, in a certain amount of time it'll travel this distance, so this is a distance, that is equal to c times delta t. But that also would tell us the volume of electromagnetic radiation would pass through that. So that would actually be U times the area times c delta t would be the total amount of energy that passed through that area. And then if we want to think about the pointing vector is the energy through the area in the amount of time delta t divided by A delta t is actually equal to just U times C. And so that's important because we're trying to make a relationship between these two quantities so that we can use it later on. What's the relationship between the Poynting vector and the energy density? And again, we see that they're related by the factor of C. And so we can express the Poynting vector as epsilon naught C times E squared, or 1 over mu naught E times B. I left lots of slides for that. So now the thing about when you think about the Poynting vector and you think about the fact that it's equal to E cross B over mu naught, keep in mind that both of these quantities, the electric field and the magnetic field, these are waves and they're varying in time. And so, the value of the Poynting vector, that becomes an issue because we would look at the Poynting vector at a specific instant in time. But, depending on what time we choose, it could have a lot of variation. And so what we prefer to think about is what we call the intensity, which is basically the magnitude of the average value of the Poynting vector. And so we have the Poynting vector is the electric field times the cosine because it's a wave function, and the magnetic field is the amplitude of the magnetic field times the cosine. And when we multiply those together to give the Poynting vector, we could say, okay, well, what would the average value be? Well, we would end up that S would be equal to E naught B naught times the cosine squared of kx minus omega t. And we'd say, okay, well, what's the average value of the cosine squared? Cosine squared is going to alternate between 0 and 1 the whole way along the timeline. And so the average value of that would actually be 1/2. And so that's where we get the average value of the Poynting vector. Notice there's this factor of 2 here. And so these would be the amplitudes of the electric and magnetic fields. And the intensity, of course, just looks like basically it's 1/2 times the maximum value of the Poynting vector. And again, because of the fact that we can express the electric field and the magnetic field in terms of each other, because we know that their ratio is equal to the speed of light, there's a lot of different ways that we can write this expression. Now, the last thing that we're going to go over, just really briefly, is the idea of radiation pressure and momentum. And I like this picture because this picture sort of illustrates the fact that radiation pressure truly exists. Now, when you think about it, it might seem kind of crazy. Radiation pressure is literally the idea that light can exert a pressure on material on a surface when it hits the surface. It also, we're thinking about the idea that as the electromagnetic waves travel through space, they're carrying momentum with them. Both of these things might seem odd because it's invisible, and if we're not thinking of it as a particle, it might be hard to believe. But in this picture of a comet, you might not be aware of it, but comets actually have two different tails, and it has to do with two different processes. But one tail is the dust tail. So now, as a comet is going around the sun, it's actually sublimating. That is, it's a frozen chunk of ice, but it's vaporizing as it gets closer to the sun. And then that material, that dust and gases, are sort of surrounding the nucleus of the comet. But both the tails are being pushed away from the comet by forces coming from the sun. And the dust tail is being pushed away through the radiation pressure from the sun. And so we actually see that physically happening in space. And so I just thought that was a good sort of visual for you. When we think about the waves carrying momentum and being able to express a pressure on a surface, I want you to remember the impulse-momentum relationship, where we learned about impulse, which was a force integrated over time, and that was equal to a change in momentum, and that because of that, the idea that when an object comes onto a surface, it will be, and it interacts like, say, a ball hitting a wall and bouncing off, there's an impulse that the ball exerts on the wall, and vice versa because of the third law. And because of that, the ball will experience a change in momentum. So similarly, if we believe that electromagnetic waves are carrying momentum, when they hit a surface and interact with it, they will absolutely exert a force on that surface. Therefore, they will exert a pressure on the surface. And we do actually see this, even though the pressure is very, very small. In the previous picture with the comet, because of the material or dust particles, it's very easy to see them be deflected. But we can also just use, think about solar panels on a satellite up in orbit around the Earth. We'll actually feel a radiation pressure from the sunlight coming from the sun. Now, if you remember, when we talked about the impulse-momentum relationship, there was actually two scenarios, sort of the endpoints or the extremes. When an object hits a surface and bounces off, we learned that a greater pressure would be exerted than if the object just came into the surface and then came to a stop. The reason the force is greater is because the change in momentum is greater. And so in general, the pressure from radiation can be expressed in terms of the energy density if it's a perfect absorber. That would be analogous to a ball hitting the ground and just coming to a stop. Or if the ball comes to the ground and bounces off with the same momentum as it came in with, that's analogous to what we would call a perfect reflector. And of course, in that case, as you remember the impulse-momentum relationship, the bouncing will give you a greater force. Likewise, you will feel greater pressure from the perfect reflector. Now, again, the U could be expressed as the electric field, or in terms of the electric field or the magnetic field, which are changing with time. So it actually makes more sense to look at, instead of looking at it in terms of U, which is related to the pointing vector, makes more sense to just think about average value and the average intensity. And so we express the pressure that a perfect absorber and a perfect reflector would feel in terms of the intensity, which is the average value of the pointing vector. All right, so that wraps up chapter 16. Again, just remember that in this chapter we were really trying to get general understanding of the behavior of light and where it comes from. A lot of the math was a little bit past the course, and so we couldn't get into the math as much. And so if you feel like you're cheating, it's okay, you're not cheating. We just want to have this under our belt so that as we go to the last couple sections in the semester where we're talking about light, we feel a little bit more comfortable.